Welcome back. This is Module 6. Today I'm going to talk a little bit about the vector network model. But before I do, I'll recap last time. You remember last time in the last video I kind of wrapped up vector analysis by talking about some of the things that you can do with your vector data to summarize the attributes or the fields, and also to calculate the geometry of your features and store numeric data about the geometry, the coordinates or the lengths or the areas of your geometry. Okay, network analysis is something that you have to use when you're trying to navigate a route from one point to another, go from one place to another. And in some cases this shows you can't get there from here, and so network analysis is where you're going to be able to determine whether you can get from one place to another and how much it's going to cost you, how hard it's going to be. Here's an example of networks in Boston, and you can see from some of these examples that it's not always a straight shot to get from a starting point in Boston to an ending point if you're driving or using the street network. So in this case, in order to go from here to here, you got to go all the way around this way to make that work if you're driving or walking on the streets. So sometimes it says you need to drive a mile to go 50 feet. So in this case you might have to drive a mile, I guess, to go from here all the way around and get to here, when you could actually walk on sidewalks maybe and get there in 50 feet. So sometimes network analysis is important because the real world isn't always straight shot. Remember in the vector analysis module I did this example problem about how much of the US is more than 50 miles from a big city, and the answer was 64%. But when you think about that, is that reasonable in terms of what question you're trying to answer? How many people have personal helicopters that live out in the rural areas that they can just get in and go directly to these places? And so do straight shot calculations that involve things like buffers, do they really give you answers that are worthwhile? And the answer is in some cases they do, but in other cases they don't. Here's yet another example. Washington State legalized marijuana probably back in 2013, and they had to decide where they were going to allow people to sell marijuana, and so they made some rules about not allowing to sell things close to schools or playgrounds. And so they made a rule that says you have to be X number of feet away from a school or a playground. Well, they decided that maybe X number of feet didn't really matter in terms of straight shot. Maybe what mattered was the path of most common travel. So if it was X number of feet of walking or of driving, that would be 1,000 feet in this case. That might be different than if you just drew a buffer around each school and each playground and said that's the exclusion area. So you can see that network analysis has applications. In the next video I'll go through some of the applications that you can use in ArcGIS. Bottom line is, sometimes as the crow flies is not really a realistic way of modeling the world. So what's a network? It's a system of interconnected lines and intersections that represent routes from one location to another. Okay, so it's lines and intersections. The intersections you can think of as points. When you're talking in network terminology, the lines will be called edges and the intersections will be called junctions. So you've got to remember this network terminology. Edges and junctions are the equivalent of lines and points. These networks can be human-made or natural, or maybe a combination of the two. As an example, roads and utilities, those are generally human-made networks. And maybe game trails and streams, those might be natural networks. They're paths or routes from one location to another. Network can be undirected or directed. Usually you think of a transportation network as undirected. You can go in both directions on most of these edges, which are the lines. Or a geometric network, that's generally a directed network, and you can think of that as something like a utility network or something where things are flowing in one direction only. When you look at the ARC catalog representation of what these networks are, you can see that they're all going to be stored in feature data sets. And you can remember from earlier videos that a feature data set is a collection of feature classes that all have the same projection. Remember, feature classes are collections of features that have the same projection, and they're going to have the same attributes too. So the key to this is you're storing things in a data set, which is going to allow you to use topology to do things like connectedness. And so in a network, the points and the lines, which are now the intersections and the edges, are going to be connected, and you're going to use topology to enforce that connectedness. There are other types of feature data sets that you might use, a terrain data set that allows you to model the terrain. Here the network data set is what you store the transportation network in. A geometric network is what you would store like a water utilities network in. And there's another type of data set that you can use to store partial information, which is called the partial fabric. Okay, here's an example of a geometric network. This is a water network, a water utility. And so you can see that there are lines, which in a network are going to be called junctions. There are water main lines, and there are water service lines going off to the individual residences. So each one of these is a feature class that's stored in a feature data set. You can see here's the shape field, so that's where all the geometry information is stored that you can pull out by doing calculate geometry and store it in fields if you want to. It's got other attributes associated with it. There are also junctions, which are points that are where the valves are at that break each service off from the main line, and you can see that that's a feature class too. And using topology, because you're in a feature data set, you can do that. You can force these valves or junctions to be connected to both the water mains and the service lines. So if you were to edit or create this data, you would be forced to make service lines connect at a junction to the water mains. Here's a graphic that shows a transportation network. That's going to be called a network data set in ArcGIS, and you can see we have a point 1 and a point 2, and the network is going to give us a path to go from point 1 to point 2. This comes from your book. This is the same figure. The book has a process that's involved in building and analyzing a network, and you can see that it's a pretty involved process that involves collecting information, building the network data set, which means you're going to employ topology to make sure that the edges and the junctions are connected. Then you can go through any one of a number of network analyses to answer questions you might have about that network. And then you're going to tell the geographic story by presenting your results in a cartographic display, or maybe even just route instructions. This is an example of a transportation network and some of the things that need to be included in one of these networks. So you can imagine that a transportation network might include one-way streets and two-way streets. So it can be undirected, but you can enforce a single direction in a street. So your edges or lines are going to need to store information about whether something's one-way or two-way. When it comes to junctions, you're going to need to know whether you can make left turns or right turns, or if there are traffic lights, what type of delays there might be at each one of these junctions. Go back to the edges, you might need to know what speed limits are, and if you have barriers so that a street doesn't allow you passing along it, you're going to have a barrier junction. So junctions aren't necessarily at intersections of different edges. You can have junctions that are along a line. A lot of elements. You can see where it gets really complicated. Generally, the way that most people work with networks is they access a network that someone else has made. There are some networks that are available through the census data that you can use that will allow you to do kind of rough calculations, network analyses, without having to develop this stuff yourself. Okay, in ArcMap, you're going to use Network Analyst to do any of these analyses on a network. And Network Analyst is an extension. You probably already know about extensions. Those are kind of add-ons to the basic ArcGIS, add-ons to ArcMap. And here Network Analyst is one of the ones that you'll use. Once you enable that extension, if your license enables you to use that extension, you'll have access to the Network Analyst tools, and you can see that there are a whole bunch of tools you can access to help you build and analyze networks. Okay, so one of the main things you use a network for is to identify an optimum route, okay? And that's one of the network analysis tools you can use, identify optimum route. There it is right there. An optimum route in general is usually considered the shortest path. Now, it might be shortest in terms of mileage. It might be shortest in terms of time. Really what you're thinking of, should be thinking of as a minimum cost or a minimum impedance. What's the easiest way for me to get from point A to point B where you get to define easy and hard in terms of long, short, quick, things like that. Okay, so how do these networks work? Well, there are algorithms that go out into the network and do a bunch of calculations and do their best job to optimize routes from one point to another. But there are so many complications in these networks that it's impossible to actually calculate the single optimum route without spending an inordinate amount of time. So the algorithms that have been developed are really good at giving you a very quick, fast guess. But they all kind of basically boil down to using a method that's similar to the one that I'll try to walk you through here. So here we have a network, and it's made up of a series of junctions and edges. Junction, 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 edge, edge, edge. These red numbers are the impedance. You might think of those as distance or time or cost of some type. And so we have node 1, which would be a junction number 1, and we're using a network analysis tool to try to figure out what the minimum cost is to get to node 1 from all the other nodes in the network. So you can walk through this one step at a time. First thing we do is we say, how do I get to point 1 from either point 4 or point 2? Well, if I go from 1 to 4, the cost will be 7. If I go from 1 to 2, the cost will be 9. So the best way to get to point 1 is to come from point 4. Okay, so now I have 1 and 4 cemented. Okay, now I want to try to get to point 1. I can still go through point 2, or I can go through point 4 and go to point 1. So I can go from 1 to 2. That's going to be 9 units of impedance. I can go from 1 to 4 to 5. And that's going to be 20 units. I can go from 1 to 4 to 2. That's going to be 15 units. The minimum impedance there is 9. So now I know that 1, 2, and 4 are all locked in my network. I know the easiest way to get to 1 from those places. I can extend this and say, okay, now I'm going to get to point 1 through either point 4 or point 2. How do I do that? I can go 1, 4, 5. I can go 1, 2, 5. Or I can do 1, 2, 3. The minimum of those is 19, which would be 1, 2, 5. So now I've locked in points 1, point 2, point 4, and point 5. Now I have one more to do. I can go from 1 to 2 to 3. That's going to be 20 units. I can go from 1 to 2 to 5 to 3. That's going to be 30 units. So 1, 2, 3 is the best way to get there. And so using all that information, I see that the shortest path from point 4 to point 1 is going to cost me 7. The shortest path from 1 to 2 is going to cost me 9. Shortest path from 1 to 5 is to go through point 2 first. That's going to cost me 19. Shortest way to get from 1 to 3 is to go to 2 first, and that's going to cost me 20. So in doing its calculation, it's decided that from 1 to any other point in the network, I've determined the shortest path, and here's the cost. So now if you ask me what's the shortest way to go from point 1 to point 5, I'm going to be able to look in my table and say 1, 2, 5, that's the way you should go. That's your driving directions. Go to 2 and then turn and go to 5. So that's kind of what the algorithm behind the scenes is doing when it's doing these network analysis problems. Okay, that was pretty quick coverage of network analysis. This is kind of an advanced topic, and you can see from the complex data sets that you need to build and some of the complex analyses that you're going to need to do that it's maybe kind of an advanced topic. So we're just going to cover the surface of this in this class. There's a follow-on class to this called Geography 475 where you'll spend more time working with networks. Next time what I'm going to try to do is quickly go over some of the applications for network models and network analyses that are used in the real world, and you can see that it's really valuable being able to do network analysis because you can save people a lot of time and money. Okay, so that'll be next time.